equals more accurate. So just something to keep in mind that when you as a scientist are looking at running an experiment and trying to approximate the area underneath the curve, that if you're like, well, if I did it to an accuracy level of 2, I would get a certain level of approximation. But if I did it to an accuracy level of 1 or an accuracy level of 0.5, making even smaller trapezoids there, it would be a little bit more work. But if you can create a program on Excel that just kind of like goes through and finds these values and formalizes this process, which there is a formula, so you can formalize the process, then your approximations can get a lot quicker. And the idea of the limit as your spacing gets closer and closer to 0 would end up giving you your integral, your exact integral. All right, so we have got a couple examples to practice before we're done with our notes for today. A medical test for diabetes measures glucose concentrate in the patient's bloodstream to determine the patient's glucose tolerance by calculating the total area under the curve. After a patient is given a glucose solution, the following data are collected. Estimate the area under the curve for this patient. So we can maybe try and connect some of the things that we did above in regards to, we had a graph, which was nice to be able to kind of visually represent the idea. We also had a table, and we could have grabbed all of these numbers just from that table without having the graph, right? This 12 plus 17, we just added our 2 y values. And same with 17 plus 18, we just added our next 2 y values. And it was always just 1/2 times the distance between our x values. So we could do that same thing here. 1/2 times the distance between our x values, well, that's 0.5. And then the y values that we add are 95, 150, and then 150, 125. But I like to visually understand. And so I think that sometimes just drawing a really quick graph, what I call a poor man's graph, which is a weird saying, to kind of just really quickly have a diagram that I can write on, that I can split things up, that I can have like a nice visual representation and figure out what I'm doing. I have spacing of 0.5, so I'm going to just kind of 0.51, 1.52. I notice that I start at 95 and I end at 150 in regards to my y-axis of like what my values are going to be. 125 is less, 110 is less, 100 is less, right? So I'm going from 95 to 150. So if I do like 90, 100, 110, 120, 130, 140, 150, I can just kind of quickly put some points here. And notice I did the little hiccup because I just skipped a bunch of values to get to this point. And then I'm going to go ahead and plot these. So at 0, I was at 95. So halfway between there. At 0.5, I was at 150. At 1, I was at 125. So like here-ish. 1.5, I was at 110. 2, I was at 100. So it doesn't have to be the best, most accurate graph you've ever drawn, but it's kind of this nice, quick visual representation. I think we enjoy being able to look at a graph and be like, oh, so it spiked a lot at first, and then it slowly starts to go down, which makes sense that when you first insert something into somebody's bloodstream, it quickly goes up at the very beginning, and then it starts to dissipate with time, which is the whole purpose of why we put stuff in there. All right, so a few things to keep in mind, that the height of our trapezoids are going to be the distance between each trapezoid, right? So if I wanted to go in here and segment out what my trapezoids would be, the height of each of them is going to be 0.5. And then remember that our bases are just the y values, which are written up here. Okay. I'm going to call this area 1, area 2, area 3, and area 4. And then I'm just going to go through and find those areas. So area 1 is going to be 1/2 times the height, which is 0.5, times base 1 plus base 2, which is just your 2 first y values. That ends up being 61.25. 0.5 times 0.5 times 95 plus 150 will end up being 61.25. Area 2. Again, a half times 0.5, right? That distance always stays the same. It has to when we create these trapezoids. You have to have that equal spacing. And then now you take your next y values. We ended with this one, but realize that that begins our next trapezoid. So we start with 150 again, and then we add in 125. 0.5 times 0.5 times 150 plus 125 is going to be 68.75. I would like for you to find the area for A3 and the area for A4 on your own. A3, again, a half times 0.5. Now our y values, we ended with 125. So 125 plus, and then that would be 110. Whereas A4 will be 0.5 times 110 plus 100. For A3, we end up getting 58.75. And for A4, we get 52.5. To get our total area underneath the curve, we just add them all up, which we end up getting 241.25. That is the exact value that I get when I add them all up, but I still put an approximation value here because it is an approximate area underneath the curve. We've approximated it by the system that we've used. And while this is an exact value that we get from the system is an approximation. And so we have to just keep that in mind. Last example for today. We're going to use the trapezoidal rule. Hopefully these are all fixed by the time you open up your computer. Trapezoidal rule to find the value between 0 and 4 of this equation right here. Trapeziums is just a British word for trapezoids, so same thing. And it needs to be 0.8 units wide. So visual understanding is key here. We don't even know what this graph might even look like. So I'm going to go to my graphing calculator, and I'm going to graph what that equation looks like. Absolute value is this little button right here where we go to for our derivative, and just absolute value is over here. And we've got 2 to the x power and then minus 8. We know that we want to find the integral, or we want to find the area underneath the curve between 0 and 4. So I'm going to quickly go change my windows to encompass that. So I'm going to go from -1 to 5 to encompass the 0 to 4 area in a nice little spot that I can see. When I do that, I see that like maybe the y values aren't exactly where I want them to be. So I go back into my window settings and I say, all right, so y value, I don't care about the negatives, and let's have this go up to 10 and see what happens. And that seems a lot better. That like, I think 4 is right here. So we're going to end up having our entire area kind of encompassed in this situation. So we want to have trapezoids that are 0.8 distance wide. So a distance of 0.8. So if I were to try and think about that, if I was segmenting out my x-axis, I would be going from 0.8 and then adding 1.8, or sorry, adding 0.8 to 0.8 would be 1.6, adding 0.8 would be 2.4, adding 0.8 would be 3.2, and then adding 0.8 would be 4. So those are going to be my segments of my trapezoid. That's how I'm going to be splitting it apart. And so that's what it means by 0.8 wide, is that all of these are a distance of 0.8. And so now I've created a segment on my graph that I've just written down that represents that distance. So in order to know, like, okay, I understand the general idea of the curve here. In order to know like how to draw it in and what my y values are, you can either make a table of values. If you're like, I don't really want to draw a graph, I just want to write down a table of values. Totally fine. I'm going to draw a graph and label my points on the graph. So I know that I'm going to start at 0 with my trapezoid. So I first want to know what 0 is. So I just hit menu, trace, 0, enter. 0 is at 7. Okay, so I need to go all the way up to 7. Go up a couple more. 2, 3, 4, 5, 6, 7. And then I want to go to 0.8 to know what the y value goes with 0.8. And 0.8 is 6.25. So that's like right here. sorry, 6.26, 1.6, is 4.97. I just assumed like, hey, kind of close to 5, so that's where I put it. 2.4, oops, is 2.72, close-ish to 3. .2 is on this other side, and it's 1.19, so kind of close to 1. Notice that it hits the x-axis down there somewhere. So if I scroll over, you can see 0 happens at 3. So there's kind of this curve that happens that goes down here. And then it kind of goes up from there. The last distance that I need is for 8. So that would be like somewhere over here. So that looks like that. Drawing in my little heights, again, realize it doesn't have to be perfect. This is not my best graph ever, but it's like a nice way to have just like a nice visual representation, a diagram that I can draw on and understand things a little bit better. A1, A2, A3, A4, and A5. So we've got a total of 5 areas here that we need to find. But they all have a distance of 0.8 as your height. So A1, 1/2 times 0.8. And then adding in my y values, 7 plus 6.26, right? So we multiply 0.8 by 1/2, and that's 0.4. Multiply 0.4 to the sum of these two values, and we get 5.304. A2, we would do 1/2 times 0.8. Again, taking our previous y value and adding on our next y value, which is 4.97. We get a total of 4.492. Okay, so that same height every single time, always multiplied by 1/2. And then all that changes from each of these areas is that we take the previous height and add on the next one. So we went from 6.26 to 4.97. For the next one, we're going to do 4.97 to 2.72. And we're going to continue with those. I would like for you to go ahead and find the rest of these areas. For A3, we get 1/2 times 0.8 times 4.97 plus 2.72. And that should give us 3.076. For A4, it would be 1/2 times 0.8 times 2.72 plus 1.19. And that gives us 1.564. For A5, 1/2 times 0.8, and then the heights that we add are 1.19 and 8. And that should give us a value of 3.676. So to find the total area, we add those guys all up. I'm going to do an approximate symbol because we know that this is not an exact area underneath the curve. And we get 18.112 as our approximation. So our next lesson is going to be taking all of this ideas and taking this whole process and just trying to shorten the process because there's a lot of repeats here. Notice the 1/2 times 0.8 is repeated every single time. The heights that we add in every single time, there's like a lot of repeats that go in there. So there's a formula that we can use that's in your formula packet that just kind of eliminates some of the repeats here and just really condenses the process down a little bit. And that's going to be our last set of notes. All right. Good job today.